Okay, so another lecture in your calculus course. So by the way, so we were looking at partial differential equations, and I have not talked about how do we solve first order partial differential equation, because it's not very difficult actually, right? It's fairly straightforward. So I left it, especially Char-Pit method is there. Okay. So we looked at these special partial differential equations are pretty useful actually. So especially heat equation, wave equation, and Laplace equation, and how do we solve them using a method developed by Fourier, method of separation of variables. Okay. So I think I will do one example completely in front of you, and then the similar approach is there for other two equations. Okay, so which can be solved easily. So I leave it to you to complete the rest of the stuff, right? And after that, if time permits, I hope it will be there, we can start Laplace transform. So Laplace transform is very beautiful transformation, and I think as I mentioned in the beginning of the class, probably in your third lecture, when we talked about different transforms, Mellin transform, Laplace transform, Fourier transform, Redan transform, right? Each of these transformations have wide variety of applications. So in fact, I will show you, after introducing Laplace transformation and some of its properties, I will show you how this can be used for solving certain differential equations, both ordinary and partial. So it's another easy way to solve these differential equations. Transformations को आप ऐसे समझिए कि there is a problem in one domain. You sort of transformation means you are moving all that into some other domain where it becomes easy to solve, and then you can come back. Okay, so that is a key idea. Okay, and they have got lot of applications. So essentially असली calculus अब शुरू होती है. तो हमने जो कुछ पढ़ा है तो background है. तो ये transformation is something really very useful. So I hope some of you will study them. For example, discrete cosine transformation is useful for JPG standard, how it is used there. Wavelet transform. You ask Hemant Patil, he loves wavelet transform because, it has wide application in speech processing, right? Signal processing, right? So all these Fourier transform is really very important. And see, Fourier transform is just one thing, then there is a discrete Fourier transform, then there is a fast Fourier transform. Means the computation is faster, right? So the algorithm has been improved. And because these things have a lot of applications, especially spectral analysis is something which is very useful. For example, if you want to look at the sky and you want to know what kind of element are there from the light that is coming, you can do the spectral analysis of that. So these transformations are very useful there. Similarly, if you look at inside your body and if you extract the DNA out of it, and I want to know that at which particular portion of the DNA there are instructions for making proteins. So I can take the data of ACGT, convert them into numerical data by certain maps, and then we apply the transformation. Okay, so many times people have seen that if there is a gene, means instructions for making protein, you observe a peak in the spectral analysis, right? So those kind of beautiful applications are there, endless applications. So applications ki basically real, so calculus का real use in transformations में ही है. And I think अब तो कोर्स खत्म हो गया, तो आपको अपने आप ही पढ़ना पड़ेगा, पर मैंने आपको लिस्ट दे दी है. I think you should definitely look at these transformations and these properties, like Mellin transform, Redan transform. Redan transform, I have told you how it is used in computationalized tomography, CT scan. सबने कराया होगा CT scan, right? MRI scan. ये सारी टेक्नोलॉजी इन ट्रांसफॉर्मेशंस पे ही बेस्ड है, राइट? सो इट्स वेरी यूजफुल. एंड सिग्नल प्रोसेसिंग में, इमेज प्रोसेसिंग में, वाइडर यूज है, राइट? सो आई थिंक That's all about application. But anyway, so let us look at a special partial differential equation that we were looking at. By the way, I'm going to do one example. There are three problems, right? Heat equation, wave equation, and Laplace equation. These are three special partial differential equations. I'm going to solve only one. Two I am leaving for you, okay? But I will tell you what are the. I will give you the hint, and I want you to solve that. By the way, most of these things are taken from this book, okay? So this blue book, because it has a lot of examples for you. So you can look at it, right? Jan, Anger, Jan. Okay, so where we are. Yeah. So these are the special partial differential equations. See, this is one dimensional heat equation. Del U over del T is equal to C square del square U over del X square. Heat equation is also quite useful in, for example, in your financial stock market. So see, these equations capture certain natural phenomena, right? And so they have wider applications, right? So it all depends what you want to study, where you want to study, and sometimes you can modify or add certain terms to get more accuracy of the event. Okay. Then there is this is two dimensional. Similarly, you can have three dimensional. I mean, del square U over del Z square, right? X, Y, Z. Okay. So this is the heat equation. This is the one dimensional wave equation. Similarly, you can have two dimensional wave equation, right? And so on, and three dimensional wave equation as well. And the Laplace equation you are familiar with. If your f of z is analytic inside inside domain D, then the component functions are harmonic. They satisfy this Laplace equation, right? That you have seen. Okay, so all these three equations, the technique of solving them is method of separation of variables. What you do? The solution, two independent variables are there, right? So u x y is product of only x and only y. Assume that is the case. Then you substitute into the equation and solve. That is the thing, right? So that will give you certain ordinary differential equations. So basically, once we assume this is structure of the solution, we substitute into the equation, we get a bunch of ordinary differential equations, we can solve them, and then we can arrive at the answer. So let me start with one example, okay, and then let us see how it goes. Okay, so suppose I ask you to solve del square u over del x square is equal to 16 del u over del y. Okay. So as I mentioned, suppose solution is of the form only function of x and only function of y. So solution is product of two functions, capital X and capital Y. Capital X is only function of x, capital Y is only function of y, right? Then we substitute this thing here. So what will happen? X double prime y is equal to 16 x y prime. This prime means differentiation with respect to x, right? And so when we are looking at x, it is differentiation with respect to x. When y prime means differentiation with respect to y. Okay, that's the thing. So this implies that x double prime divided by 16x is equal to y prime is equal to y. Okay, so these should be sort of same. So I called, suppose this is, so this is the only function of y, right hand side is the only function of y, and this is the only function of x, right? This is a function of x alone. This is function of y alone, right? So we say that suppose this is some constant lambda, and once we are done this is a very important thing. Since left hand side is function of x, this is function of y, So the ratio should be some constant. Now once we have this constant, the entire thing now, so that once we assume this is a constant, that means from this expression and this expression we will get one differential equation, and from this expression and this expression we will get another differential equation, right? One for x, another for y, and then we can solve it. That's the ordinary differential equation, right? Now this lambda, since is a constant, so there are three possibilities. What? Lambda is positive, lambda is negative, or lambda is 0, right? Only three possibilities. So one can actually look at all the three possibilities and solve the equations accordingly, right? And in some cases, not in this case, but in the other cases, you will see that sometimes only lambda negative is a possibility, and when you take lambda is equal to 0 or lambda is equal to positive, actually the system becomes inconsistent and you cannot find a solution, right? So in two other examples, you will get only lambda to be negative. But anyway, here both all the things will work. So let me show you. So case 1. Lambda is equal to 0. So in that case, x double prime divided by 16x is equal to y prime divided by y is equal to 0. This gives us x double prime is equal to 0 and y prime is equal to 0, right? So this is differentiation with respect to y. So this means y is a constant when we integrate, right? And here it will give us x is a1x plus b1. I can say constant c1, right? Okay. When we integrate twice, this is a very simple one. So this is the solution, right? So that means when lambda is equal to 0, we have got the value of x and y. So your solution uxy will be a1x plus b1 times c1. c1 को अंदर मल्टीप्लाई कर दिया, सिंप्लीफाई कर लिया, एंड बाकी कांस्टेंट को हमने नया नाम दे दिया. So this is the solution. So solution is this when lambda is equal to 0, right? That is case 1. Okay. Now we do second case, case 2, when lambda is positive. And actually I will assume that lambda is kind of square, because you see the solution looks a bit nice in that case. So say lambda is equal to k square, positive. Okay. So in that case, first equation will give us x double prime minus 16 k square x is equal to 0 and y prime minus k square y is equal to 0, right, from that expression. Now this is a second order linear differential equation with constant coefficient which is homogeneous. You know how to solve it. I am writing the solution right away directly. a1 times e raised to power 4k x plus b1 times e raised to power minus 4kx. Okay, auxiliary equation निकालोगे, root निकालोगे, real distinct है, so solution कैसे निकलेगा, right? And this case, so basically this can be further simplified, that x of x is equal to, again using formula for, so you know that Euler's theorem is there, right? That e raised to power I theta is equal to cos theta plus I sin theta, right? So using that formula you can find expressions of cos theta and sin theta in terms of exponentials, right? I hope you remember that, right? Similarly, there is a expression for hyperbolic functions, okay, in terms of exponentials. So that means this can be simplified to with some new constants, a2 times cos hyperbolic 4kx plus b2 times sin hyperbolic 4kx, right? So that is the solution. So that means, and what about y? Y of y is constant times e raised to power k square y. So uxy actual solution is a2 cos hyperbolic 4kx plus b2 sin hyperbolic 4kx times c1 e raised to power k square y. If we simplify, this becomes a times cos hyperbolic 4kx plus b times sin hyperbolic 4kx times e raised to power k square y. Right? Baki c1 into a2 is a, b2 into c1 is b, new constants, right? So this is the solution, right? Got it? So two cases are done. When lambda is negative, more interesting thing happens basically. So that's why that's an important case. But anyway, so depending upon lambda, we have these two solutions. Now the third one, case 3, when lambda is minus of k square, a negative number. In that case, first one will give you 16 k square x is equal to 0, and we have y prime plus k square y is equal to 0, y prime. So this will give us the first equation, x of x is a1 times cos 4kx plus b1 times sin 4kx, okay, and y of y is equal to c1 times e raised to power minus k square y, right. So uxy is nothing but a times cos 4kx plus b times sin 4kx e raised to minus k square y. That is a solution, right? So method is really very simple, right? Assume that solution is of the form product of two functions, substitute it, make two ordinary differential equations, right? In each case, when lambda is 0, positive and negative, right? And then solve. Now, in some of these cases, in the equation, initial value problem or boundary value problem is given. Means, there are conditions, right? For example, it may say that the function vanishes at the initial point and end point. That may be a possibility, right? So in that case, those conditions are useful in finding the values of these constants, because you can actually find the values of these constants by putting those conditions, say, right? Somebody may say that, okay, differentiation of u with respect to x will be, say, 5, right? So at, say, x is equal to 0. So you can substitute those things here, right? And then find out the value, right? So that will help you in solving these constants. So you can eliminate these constants depending upon the boundary condition or initial value condition, right? These are two conditions possible, right? Initial value problem, boundary value problem, right? So that is a case. So that is the trick. So let me give you two other methods. Two other equations. So I am purposefully leaving the entire thing, but I'll. Okay. So there is a boundary value problem. This is for the heat equation actually. By the way, there is a perfect physical sense why it happens. I am not going to do any of those things, but anyway, you can look at it. So I think there are many good videos available for you to look at. Zero is less than x less than L and t is positive. Okay. With initial condition ux0 is f of x when 0 is less than x is less than L, x is less than L, and u0 of t is equal to ul of t is equal to 0 when t is positive. Actually, I should maybe draw a picture. Okay, this is x-axis, and there is a flow of heat. That's why it is known as heat equation. Okay, in a bar. This is 0, this is L. So length is L. Okay, this kind of container or a bar. It's a homogeneous bar of length L, and heat flow is happening, right? So here uxt is actually temperature distribution or heat flow in the bar, in the box, right? This is uxt is a function which denotes the flow of the temperature inside this bar. Okay, and this conditions tells us that the initial temperature is f of x. Okay, initial temperature is f of x, and this condition tells us that at the beginning, at the end of the bar, its value is 0, right? Okay, so by these conditions, you can actually model. So I am not going into details how and why these equations are there. I leave it to you to actually check why this phenomena can be modeled with these equations, and these are the conditions. Okay, so this is the heat equation. As I mentioned, this is used in financial market, a lot of other places this equation appears. Okay, so basically something you are trying to model, okay, may appear somewhere else also. That's something really interesting. Okay, so as a mathematician, so I know this condition that del u over del t is equal to c square del square u over del x square, and x lies between 0 and L, and t is a positive thing, and this is the initial condition. This condition says that that t is equal to 0, right? The value is f of x, right? And at the end point, the function is 0. I mean, this temperature is 0 at the end point of the bar, at the beginning, at the end, right? So once these conditions are given, how do we solve? Again, so uxt is the solution, will be function of x times function of t, right? So this we can assume, and c square is a constant which is known as thermal diffusivity, right? So what you can do, I am not solving it now, but I am giving you a hint. Okay, this is just a hint, or do it at your t time problem. So uxt solution is product of two functions. This will give us x t prime is equal to c square x double prime t, or x double prime divided by x is equal to t prime divided by c square times t is equal to, say, lambda constant, right? Just like in the previous example. Again, three cases. Case 1 when lambda is equal to 0, case 2 when lambda is equal to k square, and case 3 when lambda is equal to minus k square, right? Just like that in previous case, right? So I leave it to you, just substitute, just solve these equations and put these conditions, right, to get. And remember, since there are conditions given, initial conditions are given, like ux0 is equal to f of x and z0t and ult is equal to 0. Using these conditions, you can eliminate the constants in the solution, right? That you can do. Okay. Okay, so this is all about heat equation. Then I can say something about wave equation. So again, there is a string from x equal to 0 to x equal to L, elastic string of length L, right? This is a string, elastic string. Okay, so अगर स्ट्रिंग को खींचेंगे तो क्या होगा? वाइब्रेशन होगा, राइट? and that vibration can be modeled through this wave equation. Okay, so model is given as del square u over del t square is equal to c square times del square u over del c square times del square u over del x square. This is one dimensional, right? And t is positive. X is between 0 and L, the length of the string, right? So again, the boundary condition is given that u0t is equal to 0 and ult is equal to 0. Why these are known as boundary conditions? Because x जो actual function है, right, उसकी दोनों boundary मतलब 0 और L पे वैल्यू दी हुई है हमको, right? This is a boundary condition because x lies between 0 and L, right? इस वैल्यू पे भी हमको मालूम है, इस वैल्यू पे भी मालूम है what is the value, right? And second thing, initial condition क्या दी हुई है? That ux0, initial condition means when t is equal to 0, right? Initial time, right? T is equal to 0 is f of x. This is initial displacement at t is equal to 0, and we are also given del u over del t x0 is equal to gx. This is the initial velocity. Del u over del t x0 is gx. Initial velocity and initial displacement, right? Both things are given to us. So this is boundary condition, this is initial condition. Using these things you can eliminate the constant. Okay, that's what it is. So again, what I need to do here, I am going to again assume that suppose uxt is only function of x. Okay, product of two functions, just substitute. You will get x times double t prime is equal to c square x double prime t, or we will get x double prime divided by x is equal to t double prime divided by c square times t. Here double prime in t means differentiation with respect to t, right? The second variable. Suppose this is constant. Three cases, lambda is equal to 0. Second case, lambda is equal to k square. Third case, lambda is equal to minus k square. Actually you will see that lambda is not equal to 0. I would say that not possible. Sorry. And this is also not possible. This is the only possibility. Right. How will you show that not possible? करना है तो अभी कर सकते हो. I can, if you do want to solve it, just substitute, solve it. अभी क्या होगा? When lambda is equal to 0, from here you will get something, the value of x, right? And when lambda is equal to k square, lambda is equal to 0, from here you will get something, right? उन दोनों को डाल करके you will find uxt. Then the conditions, boundary condition, initial conditions are given there. When you substitute those things, you will see that there is a problem. I mean, you cannot, it's an inconsistent system. Okay, so that means lambda is equal to 0 is not a possibility. You will eliminate that, right? Similarly, you can do for lambda is equal to k square. The only thing left is lambda is equal to minus k square. Okay, and then the solution looks a bit beautiful, right? So, चाय के लिए भी तो कुछ चाहिए ना सेमेस्टर के एंड में, क्यों? So at least सर्दी भी हो गई है आजकल तो, हाँ? So and third and last equation is Laplace equation. Del square u over del x square plus del square u over del y square is equal to 0. X lies between 0 and a and y lies between 0 and b. So actually एक rectangular thin plate पे temperature distribution is studied through this equation. So I am not going through the physical significance, but there are some boundary conditions given that u0y is equal to 0 and uay is equal to 0, y lies between 0 and b, and ux0 is f of x, uxb is some other function g of x, where x lies between this. Okay? So these are the boundary conditions given in this case. So again क्या करना है? Suppose uxy is product of x and product of y, I mean product of x and y functions. Then we actually substitute. You will arrive at x double prime y plus x term y double prime is equal to 0. This implies that we will have x double prime divided by x is equal to minus y double prime divided by y is equal to lambda, say a constant. Again case 1 lambda is equal to 0, case 2 lambda is equal to k square, case 3 lambda is equal to minus k square. Again you can see that depending on the conditions this is not possible, this is also not possible. Okay, only this thing is possible. और तो जैसे बोलते हैं ना सुंदरकांड में अध्याय खत्म, सो ये पार्शियल डिफरेंशियल इक्वेशन का अध्याय खत्म हो गया, राइट? सो नाउ दैट इज द की थिंग. हमने केवल एक ही चीज करी है, हाउ डू वी सॉल्व दिस 3 इक्वेशंस, राइट? अप्रोच सिमिलर है इसलिए आई एम नॉट रिपीटिंग, एवरीथिंग इज सेम, राइट? हाउ वी डिड इन वन एग्जांपल, राइट? You can just solve the 3 cases. Okay, because of the boundary condition, initial condition, sometimes the equations are inconsistent, right? So for these 2 cases are not possible at all, right? So you will get the last case, and then in that case you can actually solve the equation, right? So that's all about partial differential equation. So अभी तो बहुत time है ना, so we can start Laplace transform, right? Okay, so as I mentioned, I am going to give you some definition and properties. Normally engineering students क्या करते हैं, इसकी टेबल मेमोराइज कर लेते हैं और उनको सीधा सीधा अप्लाई कर देते हैं सोल्यूशन सॉल्व करने में, विच इज़ स्ट्रेट फॉरवर्ड थिंग, कुछ सोचने वाली बात ही नहीं है उसमें, राइट? ये सब बहुत आसान टॉपिक्स हैं, बट ये क्यों काम करता है, इसके पीछे की ब्यूटी क्या है, दैट यू नीड टू अंडरस्टैंड, राइट? एंड दैट इज समथिंग वी डोंट टीच, बट एनीवे. सो सपोज LT means Laplace transform, not lecture theater, but okay, so this is LT means Laplace transform में जा रहे हैं आज क्लास करने, right? So ft is a function defined for non-negative t. Suppose ft is a function like this. Laplace transform of ft is defined, so actually it becomes some function, okay, it is defined as 0 to infinity e raised to power minus st ft dt. ये ft is equal to 0 to infinity e raised to power minus s. अरे यार ये लिखने नहीं देगा, लिखने नहीं देता है मेरे को कभी कभी, राइट? धीरे से लिखो, आराम से. Okay, this is the expression, right? And when you integrate, you can see that integration is with respect to t. So overall, whatever is left is a function of s, right? So basically, we say that t variable will become s variable, right? Something which is function of t will become function of s because ये integration with respect to t है. अब सबसे पहले प्रश्न ये उठता है कि ये हर बार हम क्या ये इंटीग्रेशन निकाल पाएंगे, बिकॉज दिस इज इम्प्रॉपर इंटीग्रल, राइट? यू कैन सी दैट. प्रॉपर इंटीग्रल इम्प्रॉपर इंटीग्रल पढ़ाते हैं जेई में कि नहीं पढ़ाते हैं? कोटा में पढ़ाते हैं ना. तो कैन वी ऑलवेज फाइंड दिस इंटीग्रल? नहीं मालूम? सो हर बार इस फंक्शन का तुम नहीं निकाल पाओगे इंटीग्रेशन. सो वी कैन फाइंड ओनली, so there is some condition on function mod of f is less than equal to constant term. We call it as a exponential order function होना चाहिए. So let me give you that definition. But anyway, before that, let us see. So the convergence of this integral is important anyway. Okay, and we can also say that inverse of this is f of t. Inverse Laplace transform. ये काट ही देता है बिल्कुल चीजें ना. Inverse Laplace transform, right? So ft लिया, fs आया, इसको इन्वर्स करेंगे तो ये आ जाएगा, राइट? सो नॉर्मली व्हाट दे डू, दे मेक ए टेबल यूज करके सीधा सीधा कैलकुलेशन कर लेते हैं, राइट? सो लेट मी शो यू सम प्रॉपर्टीज. फर्स्ट ऑफ ऑल, ये सारी प्रॉपर्टीज आप किसी दिन शाम को चाय पे प्रूव कर सकते हैं. सो आई एम नॉट गोइंग टू प्रूव इट. इंटीग्रल ही तो है, राइट? फर्स्ट इज लीनियरिटी, means Laplace transformation of alpha times f of t plus beta times g of t is same thing as alpha times Laplace transformation of f of t plus beta times Laplace transformation of g of t. राइट, आसान है प्रूव करने में, राइट? क्या करोगे, खाली इंटीग्रल की वैल्यू रखना है, राइट? अल्फा टाइम्स एफ ऑफ टी प्लस बीटा टाइम्स जी ऑफ टी यहां पे जब आएगा, right, you expand, right? It's easy, integrally. So this is linearity. Second property, ये important है, Laplace transformation of e raised to power at. क्या होगा, कोई बता सकता है मेरे को? फॉर्मूला लिख दूं. Laplace transformation of ft is 0 to infinity e raised to power minus st f of t dt. बताओ क्या होगा e raised to power at का लाप्लास ट्रांसफॉर्म? बताओ कोई क्लास में. हाँ, नहीं वो तो है, फाइनल आंसर बताओ ना s के फॉर्म में. अब जेई का कोटा, कोचिंग, इतने पैसा खर्च हुआ माँ बाप का, फिर अगर इंटीग्रेशन नहीं कर पाओ तो क्या फायदा, राइट? इंटीग्रेशन करना है और तो सिंपल है ना. कौन है क्लास में जो निकाल पाता है? e raised to power minus of s minus a times t dt. इंटीग्रेट करेंगे, एक्सपोनेंशियल का इंटीग्रेशन तो क्या आएगा, एक्सपोनेंशियल आएगा या डिफरेंशिएशन? तो डिफरेंशिएशन होता है, एक्सपोनेंशियल का इंटीग्रेशन क्या होता है? एक्सपोनेंशियल होता है. तो आंसर बताओ फिर क्या आया? हाँ, नहीं, गलत है, इंटीग्रेशन भी नहीं आता. नहीं, हे राम, क्या होगा इस देश का? क्लास में एक बच्चा नहीं जो एक इंटीग्रेशन कर पाए. हाँ, करेक्ट, 1 over s minus a, 1 divided by s minus a. देखो तुम एक इंटीग्रेशन नहीं निकाल पाते हो यार. तो सोचो कोटा कोचिंग में जाके क्या फायदा, एक तुम इंटीग्रेशन नहीं निकाल पाए, राइट? सो दिस इज नथिंग बट 0 to infinity e raised to power minus st e raised to power at dt is equal to 1 over s minus a. Obviously here s is greater than a. Okay, so this is Laplace transformation of exponential. इंजीनियरिंग के स्टूडेंट्स क्या करते हैं, टेबल में e raised to power at का इंटीग्रेट का लाप्लास 1 over s minus a होगा, याद कर लेते हैं, राइट? जेई के एग्जाम की तरह बिना अंदर बीच का समझे हुए, राइट? फाइन. Okay, third, what will be the Laplace transformation of 1? कौन बताएगा आंसर? हाँ, लाप्लास ट्रांसफॉर्मेशन ऑफ 1 क्या आएगा? -1/s, 1/s आएगा ना. देखो अभी तो मेरे को इंटीग्रेशन मैंने छोड़ दिया है, तो तुमको लोगों का इंटीग्रेशन करना पड़ेगा रिवाइज. हाँ, Laplace transformation of 1 is this. So whenever we say that Laplace transformation of 1 is this, I can always say that inverse Laplace transformation of 1/s is 1. ये this is by default, right? Okay. Next, fourth, Laplace transformation of t. t कितना होगा? Laplace transformation of t. So e raised to power minus st times t dt. तो कैसे करेंगे? इंटीग्रेशन बाय पार्ट. फर्स्ट फंक्शन इंटू डिफरेंशिएशन होता है, इंटीग्रेशन होता है, मैं तो भूल गया, मैं तो कभी करता नहीं इंटीग्रेशन अभी आजकल. हाँ, इंटीग्रेशन बाय पार्ट्स का फॉर्मूला याद है? तो बताओ आंसर क्या आएगा? हाँ, 1/s². किसने बोला? हाँ, करेक्ट. जेई का एग्जाम दोबारा देने की जरूरत है सबको ना. एक बार मैं हमारे क्वेश्चंस लेने की कोशिश करी थी, मतलब आई वांटेड टू गिव टू ऑल बट जेई में ना, व्हेन आई वाज एट IIT, बट आई थिंक वो हमारे क्वेश्चंस करोगे तो तुम्हारा जेई में रियली में अच्छा लगेगा, राइट? सो एनीवे, सो ये इंटीग्रेशन जो है ना 1/s², s is positive. Fifth, Laplace transformation of sine hyperbolic, Laplace transformation of sine hyperbolic wt. इसको करने का तरीका क्या है? एक्सपोनेंशियल में एक्सप्रेस कर सकते हैं, राइट? और फिर अलग अलग निकाल लेते हैं. तो दैट इजी वे, आपका ये वैल्यू आएगी ओमेगा डिवाइडेड बाई s² माइनस w², s इज ग्रेटर देन w. सिक्स्थ, लाप्लास ट्रांसफॉर्मेशन ऑफ cos at कितना होगा? s डिवाइडेड बाई s² प्लस a². ओके. Similarly, you can find sin at, cos at, whatever you want, right? So all these are easy formula. So question है कब निकाल पाएंगे, कब नहीं निकाल पाएंगे, right? So I should give you one definition. A function f of t is said to be exponential order alpha if there exists constant alpha and capital M such that M is positive, such that absolute value of f of t less than or equal to constant times e raised to power alpha t, where t is non-negative. T is non-negative. M times e raised to power alpha t. If we can do this, then we say that function is a exponential order, and ये condition बहुत important है. So then, when the Laplace transform exists, if ft is a piecewise continuous function on interval 0, infinity and is of exponential order alpha for t to be non-negative, then Laplace transformation of f of t exists. So what do you mean by Laplace transform exists? Means the integral की value निकाल पाएंगे, convergent होगा integral, right? If this condition is ft is piecewise continuous function and is of exponential order alpha. अगर मेरे को Laplace transform जब पढ़ा होता है तो मैं ये फैक्ट प्रूव करने की कोशिश करूँगा, वो एक इंटरेस्टिंग चीज़ होगी. इंजीनियरिंग वाले क्या करते हैं, वो खाली टेबल मेमोराइज करके आगे बढ़ जाते हैं, राइट? But really if you want to see the BT why this is true, so assume that function is of this form and show that the integral converges. उसके लिए क्या तुम्हारे काम में आएगा? epsilon wala business, right? So that is useful. So यहाँ पे एक अच्छा टी टाइम प्रॉब्लम बनता है क्या? गिव एन एग्जाम्पल ऑफ ए फंक्शन फॉर विच function f of t for which Laplace transform does not exist. यहीं से तुम्हारी कहानी शुरू, राइट? गिव एन एग्जाम्पल ऑफ ए फंक्शन f of t for which Laplace transform does not exist. तो ये आपके लिए अभी बहुत यूजफुल प्रॉपर्टी बताने वाला हूं मैं, विच इज Laplace ट्रांसफॉर्मेशन ऑफ डेरिवेटिव. एक्चुअली अभी मैंने सारे फंक्शंस का कैलकुलेशन नहीं किया है. नॉर्मली बुक्स में या कहीं पे भी यू कैन फाइंड टेबल्स, राइट, ऑफ Laplace ट्रांसफॉर्म, राइट? एक्सपोनेंशियल, साइन ax, cos sin at, cos at, ऑल काइंड ऑफ थिंग्स, राइट? हाइपरबोलिक कभी तुम्हें दिखाया, राइट? सो ऑल दोज थिंग्स आर ट्रिवियल. ट्रिवियल है तो मेरे को अच्छा नहीं लगता है. यू कैन ऑलवेज डू दैट कैलकुलेशन. So what is important is Laplace transformation of a derivative, right? So beautiful formula and very useful also. Derivative है अगर function f of t is a function और हमको derivative लिखा हुआ f dash of t, right? इसका Laplace निकालना है. So this is this s times Laplace transformation of f of t minus f of 0. In other words, this is s times f of s minus f of 0. ये ब्यूटीफुल फॉर्मूला है, राइट? कोई कौन कौन प्रूव कर सकता है इसको? लगा दो उसमें इंटीग्रल में f डैश ऑफ t रखो और कंप्यूट करो, ये आ जाएगा. चलो मैं ही कर देता हूं तुम्हारे लिए. Laplace transformation of f dash of t is equal to 0 to infinity e raised to power minus st f dash of t dt. Integration by parts. This f of t, अरे भैया इसको तो s of t, f of t 0 to infinity plus s 0 to infinity e raised to power minus s t f of t dt. This is nothing but minus f of 0 plus s times Laplace transformation of f t. हो गया फॉर्मूला, राइट? अब इंटीग्रेशन बाय पार्ट. तो इंटीग्रेशन बाय पार्ट्स अगर नहीं आता है तो फिर अटके रहोगे, राइट? सो दिस इज व्हाट फॉर्मूला फॉर डेरिवेटिव. आई थिंक दैट्स ऑल फॉर टुडे. नेक्स्ट क्लास में वी विल कंप्यूट सम मोर फॉर्मूलाज फॉर Laplace ट्रांसफॉर्म एंड आई विल शो यू हाउ दिस कैन बी यूज्ड फॉर सॉल्विंग डिफरेंशियल इक्वेशंस, राइट? ओके, सो वी हैव एनफ टाइम. सो अभी 2 लेक्चर हैं तो खत्म हो जाएगा सब. उसके बाद it's all done, right? So thank you very much. See you in the next class.